So, welcome everyone to the class number 6. And in this week, I am going to discuss about the assignment of week 6 mainly, right? So, previously, I have done 5. Good evening, Venkatesan. So, I think I am audible. If any problem you feel, you can asking me. I'll stop and try to answer your questions, right? So, what I was telling that previously I have done 5 classes already. Now, in this week, I'll try to solve assignment 6. And so before that, I will try to tell you about what are the topics covered in this week, and depending upon that topics, actually questions have been asked, and I'll try to solve, and I'll try to give a hint how you can actually solve those. So basically, in this week, like this is week the continuation of scanning tunneling microscopy and scanning tunneling spectroscopy, similarly, is going on in this week. So in the week 6 practically, so that is there. So mainly how the molecular property, molecular thing mainly, it has been done with this scanning tunneling spectroscopy, and to get a better resolution, like how one can get a better resolution of the molecular orbitals, that things are there. And then follow up things like uh, inelastic spectroscopy, and how one can use that inelastic spectroscopy for getting a fingerprint, and then spin polarized scanning tunneling microscope has been discussed. And after that, basically, we have learned a very like good topic of getting electronic structures of a material by using photo electron spectroscopy, and people normally know this by PES technique, right? Photoelectron spectroscopy. And the questions are mainly from these topics that I am talking here. So mainly these topics have been asked in different way. So before going to that, we know what is like the photoelectron spectroscopy is nothing but uh, some kind of photon flash or some kind of light is actually incident on the surface, and due to the energy of the light and the intensity, some electrons are actually coming out, and this process is actually known as photoelectric effect. And mainly in photoelectronic electron spectroscopy, normally this like the not, no, this effect is actually used up, right? So this is the main thing we need to know to understand the photoelectron spectroscopy. So before going into the questions practically, I will try to give a very brief introduction and some things, some characteristics of photoelectric effect. So before, like the what is if you think about a historical development of photoelectric effect, so at first, in let's say around like in 1887 or so, uh, Harch actually performed his celebrated experiment. That is named after him only, Harch experiment. What he have done, so he was successful in producing electromagnetic wave from an accelerated ionized gas. So that means a gas, that is ionized gas, is actually accelerating, and some kind of electromagnetic wave is formed. And that is, you can say, one of the proof of wave aspect of the light, right? Some electromagnetic is wave from some electromagnetic wave is forming from some particle, some ionized gas. And also there has been a very significant observation of the same experiment. What was that? It was like uh, he noticed that a sparking is facilitated when an ultraviolet light is incident on the metallic wire. Whenever that metallic wire, like uh, to spark, like to accelerating the ionized gas, some kind of wire connection is there, and whenever ultraviolet light is actually incident upon that, there is a sparking kind of thing, some kind of sparking. So that means that character, the particle character of light is actually there in that process. So this is very like primitive experiment you can say, like now you can say this is a kind of photoelectric effect also, but this is the first beginning. And then mainly it comes in the form Leonard, sorry, Leonard is a very big scientist, and he done an experiment. What you can say the most primitive experiment or the first experiment of photoelectric effect. Einstein, normally people know that photoelectric effect is actually observed first by Einstein. That is not the case. He actually explained. People have observed it, but they cannot explain it. And Einstein actually, using the help of Max theory, the Planck's quantization theory, he actually describe the photoelectric effect, how it is, how one can describe the effects that you are showing, that is actually showing in the field, right? So that observation is basically done by Leonard. So what he have observed, so uh, in a quartz tube that is evaporated, some light is actually incident on a metal surface, that is mainly cathode, and then there is gap, basically there is no connection between cathode and anode, and there is a bias is actually given. So just giving the light, we are getting some kind of current. That means obviously there needs to be a flow of electron that needs to reach to complete the circuit, and that's why we are getting the current. That means just by putting some kind of light, one can get, actually we are getting the current, photoelectric current. So that is the experiment Leonard has done. So he got this, and then like he actually uh, get all the parameters. So how this things is actually can be, how this thing can be like vary upon the voltage, vary upon the light incident, light frequency and all. He has done all that. So what are those, like, so what we are actually doing, so kind of giving some kind of light, and obviously there is a voltage that is there, and we are getting some kind of current. So we are getting some current, obviously we are getting with respect to some voltage between anode and cathode. That means cathode is actually exposed to the light, and some kind of electrons are coming out, and that is going reaching to the anode, and that's why you are getting the current, right? So there is a voltage. So the normal thing, if you do, what will be the I versus V? So depending upon like how the photocurrent will depend upon the voltage that is applied between cathode and anode. So let me say this beforehandedly, like if you don't put any kind of any bias, still there can be some kind of photocurrent, you can get it. But like if you apply the bias, that times electron will move towards the positive end. So if you apply more and more positive bias, electron will go like more and more towards the anode, and you will get uh, like similarly, so you'll get more and more current. So that, like but if you don't apply, even depending upon the incident light and incident light frequency also, obviously you are going to get some amount of current. But with the voltage it will depend. So how it will depend, like normally with the voltage, if you plot, it is like, as I said, when the voltage is actually zero, some current will be there. Now, let me change the color for your understanding, right? And then if we apply the positive bias, it is going to increase. So let me just allow him to join. Yeah, just give me 1 second. So yeah, so I was talking about the photoelectric effect and the mainly the IV plot, right? So this will be the case. So if you, so that means what I said. if you apply more and more positive bias in the like between these two, this is, let's say, cathode and this is anode, so more and more electron will reach to the anode, and similarly you will get some positive current. So current will definitely going to increase. So now if you think, you will give negative bias, that means now your anode is negative. Let's say at first the first case is positive. Now if it is negative, then electron will be repelled, so it cannot go. So that times that current will be decrease. The current will decrease. Now after a certain voltage, so if you apply so like after a voltage that is so negative, that electron will not even go to the anode, and that time there will be no photocurrent. So this will be the case. So this is my I, and this is my obviously voltage. So normal typical I versus V plot, I versus V plot will look like this. In case of, obviously, this is photocurrent, right? And not only this, after certain voltage, this is going to be like this. I'll obviously explain what all these things. Let me just go one by one. Let me just tell you things at a certain point. So I'll tell everything. So this is I versus V plot, normal standard. Now what he has done, he has taken this with different intensity, right? Different incident radiation intensity. That means he just changed the intensity of the light and tried to see what will happen to this I versus plot. Obviously, he is keeping the metal constant. He is doing it with the same metal, just changing, keeping everything same, just changing the uh, intensity of the light. Now the plot will look like if depending upon the intensity, this is intensity of incident light, right? So if you increase the intensity of the light, that time photocurrent is actually going to increase. Basically, intensity is nothing but the number of electron. Sorry, number of photon, number of like photon. If you know about it, light is nothing but a source, like a flow of photons. So it is like that. So if you increase the intensity, normally he observed that photocurrent is going to increase. Nothing but that. And he also observed that after a certain voltage, this current is actually not increasing at all. And that voltage, he said, this is nothing but the saturated photocurrent, and that voltage is actually called saturation voltage. So why it is happening? I'll again explain that why it is happening. That is the stopping potential. After a certain negative potential, there will be no electron which can go up to the anode. And similarly, from a metal, if the light is like, let's say you are giving some kind of light, so it has some intensity and frequency, like that. So the number of total electron it can eject is obviously constant. Now if we apply positive bias, that means electrons can reach to the anode properly. Now obviously if you like increase the bias, then more electron will reach, because the bias is that high, so the all electron will be attracted towards them. But after a certain voltage, there are no electron left which cannot like reach. When all the electrons that are ejected will reach to the detector, or reach to the anode, that time, then if you increase more voltage like than that, there is no electron which is going to be there, because all the electrons already reach to the detector. So that time there will be no increase in the photocurrent. So after a certain voltage, obviously there will be no change in the photocurrent, and that is called that saturated photocurrent, or the voltage is called saturation voltage, right? So now this is the stopping potential. After, what is stopping potential means? The negative voltage, after which, like if you increase the negative voltage, after that there will be no photocurrent. And the saturation current means after that voltage there will be no increase in the photocurrent. Up to that there will be increase in the photocurrent, after that there will be no. So that is called saturated photocurrent. But he observed these things, he don't know why this is happening and all. And then he actually did what he did, like IV power plot for different metal, right? So how it will look like if we take like different metal. So what he has observed, like let's say for metal 1, let's say this is the case, and for metal 2 he observed like this. So this is for metal 1, this is for metal 2. So keeping everything, intensity and all same, keeping intensity of the light, frequency of the light, everything same. He just did like same. He just exposed same light with the different metals. This is a metal number 1 and this is metal number 2, and find this kind of plot. For this is the IV plot, same IV plot, just for two different metals. So what you observe, the saturation current, that is my saturation current, saturation current, that is same. That means in the same voltage we are getting the saturation current, but just the stopping potential, that is going to be changed. So if we vary metals, keeping intensity as constant, saturated photocurrent remains the same, but the stopping potential that become different, and that is due to different metals have different kind of work function, and that explanation I'll give again. But if you want to learn that, like why it is happening, so like each metal has a different kind of work function. What is the work function? The amount of energy that is required to eject one electron from the surface, so from the metal. So it is going to be different for different thing. So that's why it is actually different. So, and it is usually observed, what he observed actually in case of Leonard, he observed that if we increase the ionization potential, what is ionization potential? That is also nothing but the energy required to eject one electron from the valence shell. So ionization, like energy required for that, for that the last the one electron, to eject one electron, how much energy is required? That is called ionization potential. We all know that, right? So he observed that with increase in ionization potential of the metals, that stopping potential actually decreases. So if you think about like a question, let's say, sorry, sodium. Let's say if somebody asks you that potassium and cesium, who is going to have more stopping potential, right? So obviously, whenever we go down in the periodic table, that time ionization potential decreases, right? Because the size increases and all. So that means CS is actually having less ionization potential than the potassium. Like cesium is actually having less ionization potential than the potassium. So what he observed, that increase in ionization potential of the metal, stopping potential decreases. So that means CS will have, it is actually having lesser ionization potential, right? So that means it will have higher stopping voltage than the potassium. So actually, this is his observation. And then what he has done, he has done the variation of photocurrent with frequency of incident light. Now he changed, like he kept the intensity is constant for both the current, both the light. He kept the intensity constant, but just changed the frequency of incident light. And what happened? What he observed? Like what he observed? He observed like, let's say this is my I, this is my P. So he observed like, right, and the another one. So he observed like this kind of for different, like let's say this is new two, this is new one, and he observed like this. So with increase in incident radiation frequency, obviously the intensity needs to be constant. The stopping potential actually increases, and at the same time saturated photocurrent decreases. So you see this saturation photocurrent that actually decreases, and this actually increases, right? Because this is the new two and this is new one. So from new two to new one, actually frequency increase, the photocurrent decrease, and the similar thing for like then the inverse thing for the stopping potential and all. So this is his observation. So this is normally typical curve looks like in case of. So this is my new three, new two, and new one. So saturation, right? Now variation of kinetic energy. He has done also this thing. The kinetic energy of the ejected electron with the frequency. So whenever one increase the kinetic energy, with like the whenever we increase or just change the frequency of the light, how the kinetic energy actually changes. So we normally know like if we increase the frequency, right? So frequency is nothing but energy. So we are actually giving much more energy. So some energy will be spent to the spent towards the uh, that removing of the electron, and the other, the excess energy, will actually take part in giving the kinetic energy to the electron. So if we increase the frequency, obviously the kinetic energy is going to increase. But what he observed that that frequency with the kinetic energy or the right is actually giving the angle that is always same. So you are getting just changing the frequency, but the incident angle is actually constant. Just the kinetic energy is increased. So these are the observations he got. And now one more thing he has done, that is he also have seen that kinetic energy with respect to the intensity. This is, let's say, kinetic energy, and this is intensity, right? Obviously keeping the frequency constant. So whenever he kept the frequency of the light, frequency means frequency of the light, obviously constant. He just tried to visualize how the kinetic energy of the electrons actually changes, and he observed very beautiful observation. Like there is actually no change. Obviously, after a certain frequency, there is no change in the kinetic energy. So with respect to intensity, that means intensity does not affect kinetic energy of electron after a certain frequency. So obviously, if you fix that frequency, that is bigger than a value of the frequency, and normally that value is called as threshold frequency, and then the intensity is actually does not affect or that does not alter the kinetic energy of the electron. So that is what it is written. For a fixed metal, if the frequency of incident light is greater than the threshold frequency, what is threshold frequency? Below which there will be no photocarbon. Because if you increase as much intensity as you can, but there will be uh, no ejection of the electron after like below that frequency, and that frequency is called threshold frequency. That is nothing but the threshold frequency. So if you just keep your frequency higher than the threshold frequency, then the kinetic energy of the electron does not depends upon the intensity of the light, right? So I just it is that's you can then you can actually clearly see this. Yeah, let me just write this again. Intensity. Right. So this is the case. Also, then like we have observed all these things, how that metal, changing the metal, changing the voltage, changing the frequency, changing the, let's say, uh, changing, let's say, your yeah, the intensity of the light, how these things are, photocurrent is actually changing. Now, what are the explanation we get from the classical knowledge of the light? So, when a light of a suitable intensity is incident on the cathode, then it will obviously that cathode means some metal. It is going to absorb it first. It's going to absorb it, and when this energy is greater than so obviously all the metal has some metal, or all the material actually has some kind of binding energy. What is binding energy? Of like the energy required to remove an electron from that metal. So that is the binding energy of that metal. So after a certain, obviously, So that means that absorbed energy, whatever is absorbed from the light, will be used to actually electron. If that is the light, incident light, if that is higher than the binding energy, then obviously electron will be ejected, and this ejected electron can have positive kinetic energy, can have zero if that energy you are giving in form of light is same, just same as the binding energy. So then it will just eject, but there will be no kinetic energy to the electron, that will not reach to the anode and all. But if it is have some excess energy, so that will be contributed towards its positive kinetic energy, and they can reach up to the anode, right? Even if the potential difference is zero, that is the reason. Like, if your light intensity, light, sorry, not the intensity, light energy, whatever you are giving, that is absorbing, if the absorbed energy is higher than the binding energy, so the binding energy is required to remove the electron, and then the excess energy that, because that is higher, will be used as the kinetic energy, and due to that it can reach up to the anode. So if you don't put any kind of bias to the anode, still you can get some kind of current, and that is the case. That is the case. You can see. So this is the 0 point when there is no voltage. Still you are getting some kind of current, and that is due to that, right? And then when potential difference increases, the electrons will be attracted by anode. So that you can easily explain that whenever you applying more and more positive bias, then current will be more and more, because electrons will be attracted towards that anode, and then it will reach, and then we will get more and more photocurrent. Now, if the photocurrent is sufficiently high, why there is a saturation current? That is what it is, right? I already discussed all this, but just uh, sum up all the points here again. When the photocurrent is sufficiently high, so that all the ejected electrons are accumulated on anode, so it is such high that all the electrons that are ejected can reach up to the anode. So then, if you increase more and more voltage, there will be no change in the photocurrent, because there is no more electron actually to reach. So that's why you will get a saturated photocurrent, and that is called saturated photocurrent. And in negative bias, that will be repelled, and obviously that's why if you increase more and more negative bias, photocurrent will be less and less, and after a certain value of the negative potential, there will be no electrons who can reach to the anode, right? And that potential, that corresponding potential, is known as the stopping potential. But all this classical knowledge cannot explain something. Why there is a need of concept of why there is a need of threshold frequency. What I said, what is threshold frequency? That is a frequency below which, if the frequency of light is less than that, however you increase like the intensity of the light, there will be no photo current. So there needs to be a certain frequency above which only photocurrent, actually we get photocurrent, or we get the photoelectric effect. So this cannot be explained by the classical thing. And then the kinetic energy of ejected electron is independent. So if you increase intensity of the light, intensity means more and more photon, right? So if you increase the number of photons, still the kinetic energy of the electron does not depend, because kinetic energy of the electron depends upon the energy of the incident photon, which is actually colliding with the electron, right? Only that, not the number of photon, only on the energy of that photon, because we know from the quantum. So classical mechanics can also not explain this. And also, whenever there is this photon and the surface electron collision, then instantaneously electron is moving out. So why this process is such instantaneous? That also cannot be explained by the classical. So Einstein came into this picture, and Einstein suggested that light is a collection of energy packet. So light is not exactly just an wave; it is an energy packet, and each packet is called a quantum of energy, and the energy associated per packet. Let's say this is h nu. So depending upon the frequency, it is actually having some kind of energy. So this is the h nu, where h is the Planck constant, right? So when light is incident on a clean metallic surface, then there is a two-body collision between the photons and the electrons. Obviously, intensity. That means I said intensity is nothing but the intensity is light. number of photons, right? So let's say this is your metal surface. So if your intensity is such high that there is as there is many photons are there, so there will be like this one electron, let's say this is your electron, can be collided by two or three, so we don't need that one. So that's why the intensity is not too high such that two body collision is predominant, such that only only two body collision is actually happening. So in that case, obviously, if we think about the energy of the photon is h nu, so some is actually using to over some is actually using to overcome the work function that is required to reject an electron, or the you can say that is binding energy, and then the other part of the h nu is actually contributing towards the kinetic energy. So this is the explanation he has given. The part of energy is used to overcome the binding energy of the ejected electron, and the rest part gives you the kinetic energy. And this phi is nothing but the work function. That means what is work function? This is the minimum energy required to eject an electron with a zero kinetic energy. So let's say you can get it easily from this. If the phi is actually zero, so that means Ke is equals to H nu. Means the total energy is actually, sorry, if the, sorry, so if the kinetic energy of the electron is zero, that time 0 is equals to h nu minus phi. So that means phi is equals to h nu. So actually, total energy of the light is actually is using that energy, total energy, to overcome the work function. Now, if it is overcome the work function, there is no kinetic energy, so it will not move anywhere, just like come out like that. So what is work function? The minimum energy required to eject electron with zero kinetic energy. So these are the things I wanted to tell you about photoelectric effect. So now I'll just uh, go to the problems. So this is actually very basics of the photoelectric effect. So you need to know this to understand photoelectronic spectroscopy, like the photoelectric spectroscopy, that XPS and UPS, normally called as XPS and UPS. So that's why I have given this very small introduction to this. Now to today's actual um, notice, actual motive, that is like solving the questions. So let's go one by one. That is the question number one. Which among the following is are true for inelastic tunneling spectroscopy? So that is well explained by the faculty. I'll again tell you. So up to the like the week 5, or the in the very initial classes of scanning tunneling microscopy, we all know that all the collision, that is actually also not all the all the electron tunneling that is happening, that is due to that is a elastic kind of tunneling. Like there is no loss of the energy of the electron while moving. But if, let's say, your surface is actually having some kind of add atom, these are the add atoms, right? Some kind of add atom, and some energy is actually using there for some vibration or other, like some kind of dynamics. So some kind of energy will be lost, right? So instead of getting only the elastic energy, you will get also the inelastic, and that can be used very beautifully for getting, like, depending upon its vibration. So right, we know that IR spectra is nothing but the fingerprint of the molecule. It will very specific towards the how the bond strength is, and all, how the mass of the two atoms present in the molecule, all that thing. So it will be very signatural for a molecule, right? So similarly, that is this kind of inelastic scattering, right? So inelastic tunneling spectroscopy can also tell about the molecular signature very specifically. But the real problem, is a technical problem. That is, normally the percentage of inelastic tunneling or whatever, that is very less, like less than even 1%. So To find out what is actually happening towards that inner sleep, to find out the actual data in inelastic tunneling spectroscopy is very very difficult, and that's why it is not that much celebrated, right? But what is inelastic scattering, inelastic tunneling? You get it, that some kind of energy is lost due to the vibration and all. So let's try to answer this. Which among the following is are true for inelastic tunneling spectroscopy? Energy of electron never lost by tunneling. Is it true? But because that is elastic tunneling, and inelastic tunneling is basic thing is some kind of energy is uh, lost due to some kind of vibration or some kind of relaxation in the atom layer. So that is not true, obviously. Now, tunneling electron can lose their energy. That is obviously true. And I also said that percentage of inelastic component in any kind of inelastic collision, the percentage of inelastic uh, collision or inelastic scattering or whatever it is very very less. So these two things are true. So what will be the answer? A and B is not true. This is my answer. Right here also I have written the answer. So in case of inelastic tunneling, that electron can lose some energy, and that probability of that is very very less. Let's come back to second question. Which electron will eject from the material in photoelectron spectroscopy? So what is photoelectron spectroscopy? It based upon the photoelectric effect. Already told you about photoelectric effect. Here I have written that is not observed, that is characterized how it is happening by Albert Einstein, right? So this is based on the photoelectric effect. And what is photoelectric effect? That is instantaneous emission of electron from a metallic surface when it is irradiated by light of suitable frequency. Now, depending upon the frequency of the light, it will interact with the electrons in different level. So if your energy is less, it will try to collide or try to interact with the lower energy. That means that are the valence electrons. And if it is very very high, then it can go to the core electrons, right? So this is the case. Now, this is so whenever we use UV light, that is kind of lesser energetic light, that time we actually interact with the valence electrons, and if we use X-ray, that time we actually interact with the core electron, right? So, which electron will eject from the material in photoelectron? Because UV photoelectron spectroscopy and X-ray photoelectron both are coming to the photoelectron spectroscopy. So obviously, in case of UV, this is this is true for UV valence electron, and this is true for X-ray. If we use X-ray, so obviously photoelectron spectroscopy, both electron can be removed. So both valence and core. So this will be my answer. No doubt about that. Right. So both A and B. If we use depending upon the energy of the incident light, we will get what we will eject. So obviously in photoelectron spectroscopy, both the electron, like in the valence electron, the core electron, everything can be ejected from the material. So this is the schematic diagram of the photoelectronic spectroscopy. So there's a photon source. H nu is actually incident, and then photoelectrons. This is photoelectrons are coming out, and then it goes towards a, like there is actually charge, it's a plus minus, so it bends, and then there is an energy analyzer which analyze the kinetic energy of the different energy, the kinetic energy of these different electrons. And we know now that kinetic energy will be a signature of the binding energy of that electron residing in the which valence chain and all, and that can be utilized to know the information about the surface and all. So this is the schematic diagram of the photoelectron spectroscopy that I want to share with you. Let's come to the question number 3. Which of the following statements are correct for X-ray photoelectron spectroscopy? Now we already said X-ray means that is higher energy, and we already discussed that X-ray is, if it is higher energy, obviously it is going to interact with more like more inner electron or electrons with more energy or like that. So that means the core electrons, right? If the energy is very very less, then it will attack or interact the Valence electron, if it is very like it is extreme, means very high energy, so it will obviously going to interact with the core electrons, and then obviously core electrons will be ejected, and that means this is actually going to give out the elemental composition, right? Because it is going, and it can give about the, as it is actually moving the sorry, ejecting the core electrons, it can give information about the oxidation state of the metals or of the material, right? Also that means the bonding nature of the atoms, everything can be given by the XPS. So what are the options, and what is the asked in the question? Which are the correct? Provide information about bonding nature of atoms. Yes. Gives elemental composition. Yes. And one can kick electron from core level. Right. If it is for UPS, then it will be valence electron. Right. Not from the core level. From the valence orbital. Valence valence shell. So that means all the three options are correct. So that is will be my, all of the above will be my answer. Right. I think there is no doubt about this answer. Okay. So let's come to the question number 4. What are possible x-axis coordinates in graphs made from PES data? Normally, in case of PES, we always use that photoelectron count, so number of photoelectrons that are coming versus the binding energy. So that means in x-axis, always it is energy, because we want to know what is the binding energy of that. So depending upon the specific metal, or depending upon the surface kind, depending on the interaction between surface and atoms, this binding energy, that means that binding energy is going to be different, and that is what we are trying to measure. So in x-axis always there is energy. So energy can be in terms of electron volt, in terms of joules, in terms of hour. Normally in this case, these are in electron volt and megajoules. So this is that actually normally energy in any kind, and the basic standard to units are in electron volts and megajoules. So obviously this is also going to be the answer, all of the above. All right, no problem in that. So now come to the question number 5. Which among the following factors affect photoelectric effect? Potential difference between metal plate and collector. We already said this is, let's say, cathode, right? So this is a plate, and from this there is electron source. So these are the electrons, and going to the anode. Let's say this is my anode. This is my cathode. So if we put much and much positive voltage, electrons are going. So that means we are going to get much more photocurrent. So obviously, already already discussed these things, right? Also, for a fixed metal substrate, if we increasing with the intensity, photocurrent obviously increase. Frequency of the incident radiance, with increasing the incident radiance frequency, keeping the intensity as constant, that stop, like some kind of stopping potential is changes on saturated photocurrent also decreases. So he actually asking that, is that these factors affect photoelectric effect, not the current, right? Not the current. You need to understand this. The effect, obviously, depending upon all the things, some difference we are going to get, because we already discussed. If we change the car voltage, something is happening. If we change the metal, something is happening. If we change the intensity of the radiation, something is happening. So photoelectric effect is going to be altered, or going to be influenced by all these parameters. So obviously this is going to be the answer, all of that. Now match the incorrect pair from the following. So we need to know the incorrect. So molecular orbital level resolution, COT. We already learnt in the lectures that COT can actually give better molecular orbital resolution. And taking the pentasine molecule, in the last problem solving session also, I I discussed this pentasine, and that time we have seen that HOMO is like, more or less we can comment about the picture of HOMO, but the LUMO case is not that great. So that to get a molecular orbital level resolution, the tip resolution needs to be very very less. So if we use that CO, let's say this is the CO, so this is becoming more sharp, and that can CO tip can give actually molecular orbital level resolution. You can go this reference I have given. This is a physics review B paper, and you can just see the picture. You will understand. This is normal CU tip. This is a metallic tip, and this is CO tip. And means this above this Cu tip, there is just one molecule of carbon monoxide, and then here the resolution is not that great, but now the resolution actually increases, right? So molecular level, orbital level in this case also. So whenever we are using CO atom, that time we are getting actually better resolution. So molecular orbital level resolution can be achieved by CO tip. So this is true. This is not false. This is not incorrect. Now, ultraviolet photoelectron spectroscopy measure kinetic energy of electrons that are emitted from the surface. Obviously, because the electron is not that sorry, the energy of that light that is ultraviolet is not so much high. So obviously, near surface electrons are going to be ejected. So that is also true. That is also true. There is no problem in that. Now here, X-ray photoelectron spectroscopy determine elemental composition because it can eject from core and it can give the signature of that element. So obviously, this is also going to be true because we already learned that it can give the elemental composition. Now here it is written the noble metal density of state near the Fermi energy is very much corrugated. But we in last lecture you can I'll suggest you to go to the last problem solving session even I discussed, and in the lectures also in this week Sir discussed that normally in case of noble metals like Au or copper, the density of state near the Fermi energy is very very like a broad, like there is no that much change of the density of state. That's why people normally use noble metal T because there is a problem. What is the problem? That also I have discussed. That what will be the problem in STS measuring if that is not that density of state of TP is actually interfering with the actually is going to interfere with the experimental observations. So we need some kind of TP that is actually having near Fermi constant density of state, and that is provided by the noble metal. So this is not going to be true. So this is actually danger near the Fermi energy is very much constant. That if that is written, then it is true. But this is not true. This is false. So this is my answer. So this is the answer. So let's go to the question number 7. Which among the following is true for inverse photoelectron spectroscopy? Up to that, what we have learned that this is, let's say, the atomic orbital. Some light is actually interacting and electron is coming out. Now, if we can put one electron into the valence electron into some kind of empty orbital, if we can insert one electron, so then the energy like means that means it is having some energy, extra energy. That energy will come out as a form of photon. Right. This is a very basic about the inverse photoelectron spectroscopy. Now let's see we can answer it or not. Which among the following is true? So an electron eject into valence band only. An electron inject into valence band only. Obviously, it is true because the core cells are not empty. There is no place for an electron to be injected. So this is true. But obviously, if we can like forcefully, we can like put an electron. So let's say the other point, a photon inject into the valence band. So not we are not injecting any photon. We are getting some kind of photon, but injecting the electron. An electron inject into one of the electronic states and photon emits. So obviously this is more and more correct because obviously this electron is not. So this is not true. This actually I thought this is true, but this is not true because this is not the only phenomenon. After that, some photons needs to be emitted. So this is the option. If electron is injected into the electronic state and photon is actually emitted, that is what I explained. So this is going to be the answer, right? This one. Let's say we just see. So an electron is injected into one of the electronic state, and then that same amount of energy is actually emitted into a form of a photon. So never the photon is injected. Let's say photon is injected in the case of photoelectron spectroscopy. In case of inverse photoelectron spectroscopy, that is just the inverse case. So we are injecting electron and getting the photon. In case of photoelectron, we are injecting photon and getting some electron. Right? So we understand this question, right? Okay. So let's go to the question number 8. So binding energy is the measure of. We already know binding energy is the measure of. So the amount of energy that is required to remove an electron from an atom. So we don't need to explain this because we already know all this. What is binding energy, right? I'm not going to explain this. You know. Now come to the photoelectron spectroscopy. In photoelectron spectroscopy, this is question number 9. In most of the catalytic material that I just did, that's why you just need to look into this part. That is catalytic material. Then let's finish the question. The density of state near the Fermi energy is much more corrugated than the flat density like in AU111. So normal cases, if this is catalytic material, so catalytic material means it needs to be reactive, right? And we know a surface will only become reactive if it is very, very corrugated. If it is highly packed and all, then that time, if it is not corrugated, that time there will be the reactivity will be very, very less. So to become a reactive surface, to become a catalytic material in terms, this needs to be corrugated. So obviously this is true. Because the catalytic materials, these are reactive, and normally reactive surface are always corrugated, and that is the reason. Because corrugated means there will be some atoms, like normal case of in case of any surface, if you think there is actually some kind of unsaturation of coordination number, their coordination number is very, very less. Now let's say there is some kind of step or kings. Let's say this is the, so this atom is much more, or let's say there is only two, like that, some kind of kinks and steps, if these are the actually things that make a surface corrugated, and these are due to their unsaturation, due to their very, very less coordination number, these are very reactive, these are highly reactive. So that is actually true, right? So let me go to the last question, that is spin polarized STM. So what is spin polarized STM? In case of STM, we are actually using some kind of metallic tip. And in spin polarized, we are actually coating that tip with some magnetically active material. And very common example is in tungsten, the chromium is deposited, and this is for magnetically active material. And now we are actually measuring the scanning tunneling, scanning tunneling spectroscopy or scanning STM, trying to get the STM image of this copper 111. One thing to notice, in all the there are some kind of lens, some kind of add layer is actually forming, but let's say all the height of this jet, so these are same always. In all the cases, all the islands are actually having same height, but the STM is giving some different kind of, some different, these are, let's say, some high. So there is some different kind of, there's some different kind of height it is giving due to the magnetic property of the material of the tip. Because if you can see carefully, there is some magnetic polarization. This tip has some polarization, and the surface actually having some kind of polarization. Whenever these two polarization are actually opposing each other, that time it is giving lesser height, and whenever it is the other case, like both are actually like this. Let's say this is the tip and this is the surface, and another thing is this is the surface and this is the tip, and that time the height is actually higher, that time the height is actually lower, right? So this is the case we are getting. So now try to answer the question. So topography is higher when magnetization of T and surface are in same direction. Magnetization of T and surface are in same direction. And topography is lower when magnetization of T and surface are in opposite direction. That is what I said. So both A and B are correct, right? You can like try to remember this in this way. Let's say this is magnetization. So let's say this is north, then this means south, and this is again north, and this is south. So there is a higher interaction, and that interaction is making the electron density a bit higher, or the topography is a bit higher. And whenever these two are like that, so there's kind of a ripple. You can think like that. I'm telling. You can remember like that. So that time there's a problem, and that time the topography is actually lower, right? So this is just to like just a formula to remember, not like exact case I'm talking about, but you can remember these things like that. Okay. So in this class, I have discussed about a bit about the photoelectric effect, how that photocurrent is going to be influenced by the characteristics like voltage, like the incident light's intensity and the frequency, how the kinetic energy is going to be. So this is a very like important effect because this actually Einstein actually got a Nobel Prize for this, right? This is very important effect, very important phenomenon. And one can say like photoelectric effect is one of the effect which actually give like people think about quantum mechanics. So there is something beyond classical mechanics which cannot be explained totally by the classical mechanics, and one such thing is actually photoelectric effect. So this is very important. I discuss this in all the questions. So if you have guys have any question, right? So you can tell me. Otherwise, I will just stop here and we'll meet in the next class with the assignment number 7. Right? Okay, Venkat. Thank you and have a good day. Okay, I'll stop here.